Hi, this is Luan Watson, and later on there will be Eric Del Rio, and we'll be discussing the optimal PWM pulse width modulation schemes in three-phase matrix rectifiers. This paper was written by Jagneer Afsharan, David Zhu, and Ben Wu, all distinguished IEEE fellows. Just a brief agenda. We'll just introduce the topic, then go over some of the most common PWM schemes for three-phase isolated buck matrix type rectifiers and their principal operations. They go over a steady state analysis between the type A and type E PWM schemes, which we'll define. And there's experimental results of both, which they develop a prototype in the lab and test some of the theoretical portions that they come up with, and then there's a conclusion. Um, pulse width modulation and matrix converters are very commonly used right now in the industry. Um, Matrix converters are defined as single stage conversion, are converters with single stages of conversion. It utilizes bidirectional controlled switching to achieve conversion from AC to DC or AC to AC, any combination of the two. Um, an alternative to the matrix converter or subset, if you will, is the PWM rectifier. Um, they come in many different configurations. You can get buck or boost for the rectifiers, as well as single stage and quasi single stage as well, with different type of configurations depending on your application if you need isolation or not. Um, Particularly in this presentation, they'll just be discussing the buck type, which they've denoted as a, I guess, a favorable source because it allows you to have high input line voltages without the high voltage ratings that you would need for a boost, its boost counterpart. The buck derived matrix type rectifier is favorable when your DC, your output of your variations of your output DC volt is needed, and that's generally the case for like battery applications where the battery voltages fluctuate, and telecommunications. Some other benefits of that are that the buck type has a dynamic response and it doesn't have many starting problems. The matrix rectifiers inherit some of the traditional benefits of matrix converters, such as low total harmonic distortion, power factor correction, and minimal filtering. So, as mentioned, the author has decided in this paper to analyze the three-phase buck type AC to DC rectifier matrix, of course, and in this case, they're using a, uh, a topology, a zero voltage switching topology, and using as opposed to IGBTs, they use MOSFETs for bidirectional switches. The reason for that is IGBTs are generally slower and cannot operate at high switching frequencies. So you have some drawbacks there because of that. Also, IGBTs have greater conduction losses at medium power. And here, down here in this figure here, it's just showing your line voltages, which will analyze your different sectors of your PWM scheme. It's basically uh, divided into six. Your whole cycle, or if you will, is divided into six portions um, to analyze your switching sequences in each each section, which would essentially be the same for each, just repeated, but they're analyzing them in 60-degree portions. So because matrix type rectifiers are basically they utilize the same transformer leakage induction to achieve zero voltage switching. You can model these as full bridge phase shifted converters in that topology, and in doing so, you can use this space vector modulation technique, and this is how they analyze it at first, just showing the traditional way to analyze current source rectifiers. So basically, this shows you have your IX and your I1 and I2 vectors, which have different components of it. IX and IY, which are essentially your different line-to-line voltages, and it shows how as you move through the different positions of your cycle. So in this case, they'll be analyzing sector one, which is moving from 30 degrees to 30 degrees negative to positive, and it shows your different uh, switching actions that are needed. And depending on your current flow, there are two possible switching states. So if your current is positive, you're looking up here at the top vector analysis, and if it's negative, you're looking at the bottom one. So as mentioned, you have four different. There's four different switching techniques that you can analyze, which are high to low, low to high, a hybrid. Those are all for 6 segments, and then you have your 8 segment switching pattern, which is which isn't low to high or high to low. It's just switching from your active vector to your zero vector, and they switch in that case. So in order to in order to do so, what the rectifier does is it synthesizes or if you will switches your voltages to get your different line to line voltages across the transformer primary for rectification. For each active vector, there are two possible switching states, as I mentioned earlier. So in this case, they're switching from VAC to VAB in your high to low, and VAB to VAC consequently in your low to high, as well as for the hybrid portion. And then for the 8 segment, you're for the active for that cycle in which your VAB is higher than your VAC, you're staying there, as opposed to the switching techniques there is as mentioned. Um, so this is a more detailed diagram showing the different phases of the switching cycles for a 60-degree segment of your 360 full cycle. And up top it describes the different conditions that the rectifier is seeing and how it makes its transitions to get you your different transformer primary voltages in order to get your DC voltage at your load. So here you see type A would be the high to low scheme. Type B would be your low to high scheme. Type C would be a hybrid of the two. However, type C is symmetrical. Um, type D is your is similar to type C. However, it's asymmetrical. And in each segment, you have both a high to low and low to high. And then E is your 8 segment switching, which just switches from your active to your zero vectors and vice versa. So we'll discuss more about the benefits of each different switching techniques later. And the biggest thing there is the losses are actually different between the two. So even though the switching from an active vector to a zero vector are essentially the losses are pretty much the same no matter what scheme you're using. The switching from high to low is the bigger difference in this case, and we'll discuss that here. So for the circuit topology that was shown a little bit earlier, the high to low voltage transition, in order to do so, there are two turn on actions that need to occur and one turn off action. One of the turn on actions there is that zero voltage switching, which has its benefits of lower losses because of your zero voltage and zero current seen at those points. And the switching occurs, as mentioned, at low voltage, low current transition, lower the losses. And then you have your low to high voltage transition, which is favorable and is going to be the ultimate reason why the type A scheme is ended up seen as the most favorable. This is because there's only one turn on action and two turn off actions, which are at one of them are at zero voltage switching. And then the high turn on loss, there's a high turn on loss occurred to because of this, but there's only one of those, and it's because of the hard switching. So you're switching under a heavier load. So this slide just kind of gives you a detail on the circuit that was shown earlier. It shows the different switching sequences. So I'll just go over and describe some of those. So you basically start with S11, S21, 13, 26, and 16 on. So look you start with your VAB voltage at the start of the switching sequence. Um, and that is because VAB is less than VAC. So what you're doing is you'll be switching from VAB to VAC. So switches 21, 14, and 15 and 22 are always kept on. And the reason for that is so that you can have synchronous rectification and it minimizes your switching needs as well. So, and also 13 and 26 function as synchronous, first synchronous rectification. However, those are actually, those switches are done in sequence with switches 25 and 12 because they're basically complementary to them to ensure that you don't short your active and your non-active voltages together, which generally are your VB if your VB is higher than your VC or your VC is higher than your VA or vice versa. And then switches 11, before the start of the transition, you will have like switches 11 and 16 on to generate your active I X vector uh, to give you, as I mentioned, VAB across the voltage across the transformer primary. The next step here is you turn off uh, switch 26, and then what happens is the current will commutate from switch 26 to the anti-parallel diode. And as I mentioned before, you don't want to short your VB and VC. So this step is just in preparation before you turn on switch 12. And then the next step here, as you see, is you turn on switch 12, and then the last step is you turn off switch 16 to complete the transition. Um, as mentioned, the switching that occurs from VB to VC is under, um, I guess, high load or hard switching. It's basically a hard switch, so you have subsequent losses because of that. Mm.
Thank you very much, Juan, for explaining how it works. My name is Eric Del Real, and I'm going to be covering experimental comparison of the type A and type B PWM schemes. The goals for the authors was that the analysis will show that the type A PWM will have lower duty loss, minimum output inductor current ripple, and minimum switching losses compared to that of the other PWM schemes they proposed when they're using the MOSFET devices. Furthermore, a low input current total harmonic distortion THD that will be able to be achieved with duty cycle compensation. One thing to mention is that the three-phase buck matrix type PWM rectifier is equivalent to a traditional current source rectifier CSR, with the exception that the switches are bidirectional. Also is that the same scheme and methodology for the rectifier is it could be used also and implemented as an inverter. So having said that, let us continue. One of the major limitations of the duty cycle loss when operating a high switching frequency is that it generates circulating currents on the primary switches and transformer windings, which results in conduction loss and poor input current total harmonic distortion THD. The turns ratio N and modulation index MA are related to the loss of the duty cycle, which in turn it depends on the choice of the frequency the switching frequency, leaking inductance, and zero voltage switching ZVS. The author states that the duty cycle loss delta dx happen at the transition from zero vectors to active vectors due to the finite transition time depending on the value of the inductance on the primary side. Since the input phase current is produced by a IP or current on the primary side, and since the IP switching is swinging from one direction to another, the result is that the two phase currents IA and IB contain two triangles A1 and A2. This is due to the bridge X duty cycle loss in sector 1A. And this can be represented right here. This is what we're talking about, A1 and A2, A1 and A2. And this is from the phase current IA and phase current IB. These two areas are cancel each other by due to one is positive and the other is negative, but these will produce a net zero current during the interval delta dx, and it will not contribute to either input phase current or output power, but will generate losses due to circulating currents. The output voltage ripple and as well as the input THD is affected by the loss of duty cycle. If the applied duty cycle is not compensated enough, then let me show the next one. And this is what they're trying to show right here. When the duty cycle is not compensated, then we're gonna inherit more loss of duty of output voltage. Sorry about that. In order to produce the phase current with the shape of a sinusoidal waveform, the duty cycle on each phase should also have the value in the sinusoidal shape that is proportional to the phase current. So the input current, the duty cycle, must be on a sinusoidal waveform in order for the output one to have one too. However, as represented in the figure right here, the effective duty cycle, the shaded area, as we can see right here, the shaded area, the shaded line is lower than the applied duty cycle in the sinusoidal shape. Furthermore, the curve of the effective duty cycle will contain step changes which they occur in 6-degree interval. And because of the phase current is determined by the effective duty cycle, the phase current will also be distorted and will contain long frequency harmonics that will affect the THD. The maximum loss of duty cycle is obtained when the magnitude of the primary voltage is minimum, the data equals 0. As a result, the effective modulation index MA should be within the range of 0 and DSX max. Let us compare type A with type E PWM in the next image, on the next slide. The type A and type E PWM patterns, you can see that the type E has two additional duty cycle losses, delta dy. The intervals of delta dy are longer than that of the delta dx. Therefore, delta dy is associated with an error pulse where the magnitude of the primary voltage is lower. When we examine the extreme cases of data where data equals plus or minus 30, the interval of delta dy is twice the interval of delta dx. And it is represented in figures E and F, right here, where the magnitude of the primary voltage is only half of that during the intervals of delta dx, in spite of the two missing pulses on the secondary side. Also, on the primary side, there are always two pulses that are used to compensate for the duty cycle loss, as demonstrated in 12F, right here. As a consequence of these two pulses, they do not contribute any power to the output load and create conduction and switching losses on the primary side. So this was regarding the primary side correlating to the duty cycle loss. In these images, we can also see that for a given output voltage, the output inductor current ripple at steady state is determined by the off time of the secondary voltage Vd. The off time of Vd consists of the dwell time of the zero vectors and intervals of the duty cycle loss. In this slide, we can see that the output inductor current ripple of type A and type E PWMs vary with the phase angle and was due to the variable of time of Vd. A total off tie of the secondary voltage Vd is minimum and is given by what the equation 1 minus Ma, where Ma is the modulation index and is multiplied by the Ts. Hence, the current ripple of both type A and type E PWM schemes, they reach a minimum value at the data equals 0. Also, one thing to notice right here is that unlike the type A PWM that has the time of Vd divided into two intervals, the type P PWM has its time divided into 4 intervals. And this is represented right here on A and B. This is A PWM A scheme, PWM E scheme, and the interval and the interval. 4 pulses and 2 pulses and 4 pulses respectively. The type E PWM is only half of that of the type A PWM at data equals 30 degrees. The total off time of the secondary voltage Vd is maximum and can be derived as 1 minus the square root of 3 divided by 2Ma. Therefore, the output current ripples of the type A and type E PWMs reach maximum value as shown in figure E and F. On the other hand, for the type E PWM, 3 of the off intervals adjacent to the nerve pulses combine into one, resulting in a large current ripple. For instance, at the angle equals -30, two of the pulses of this on the secondary side disappear so that the off-time intervals merge into one large interval. And this can be represented right here. These three pulses merge into a one large current ripple. I'm sorry, right here. Right here, it's not hard to see. So the three of them merge into making one high spike current ripple. The authors arrived to the conclusion that by stating that the minimum current ripple in the type A PWM at angle equals 0 is higher than the type E PWM by at least twice. They also mentioned that this would be one of the deficits of the type A. Nevertheless, the maximum current ripple in the type A PWM at angle equals plus or minus 30 is smaller than that of the type E PWM. They also add that it is important to mention that the frequency across the transformer with the type E is double to that of the type A PWM. And that given that both PWM schemes have the same TS, then it follows that the lower core loss and smaller core transformer can be expected of the type E PWM. However, the type E PWM will not offer a significant benefit in the transformer design based on the maximum flux density, which is one of the most important constraints for transformer design. Also, in the neighborhood of delta equals plus or minus 30 degrees, one of the two active vectors attained is maximum magnitude, and the other vector reached to a minimum. As a consequence, both PWM schemes were able to reach maximum flux density on the transformer, even though the type A is only half the frequency. In this image, on these slides, the experimental waveforms of the transformer primary voltage Vp, rectifier voltage Vt, and inductor current ripple delta IL. And we can see that these right here are for the type A scheme, and these are the type E schemes. Also, maximum current ripple of the type E was 20% greater in that the magnitude of the type A. That's based on the author's finding and after the prototype experiment. And minimum current ripple of type A 2 times greater than type E. In this, we can appreciate the experimental waveforms of the transformer's primary voltage Vp, rectifier voltage Vd, and the current ripple. A shows this one right here. A shows the type A PWM scheme at angle equals 0, while B shows the type E at angle equals 0. C shows the type A between angles of negative 30 and 0, and D shows E between angles of negative 30 and 0. E shows type A between at angles equals negative 30, and finally F shows the scheme E, type E, at angles negative 30. The experimental comparison on the type E and type E schemes that they use are right here, and this is the quantified comparison of the duty cycle losses correlated to the angles. In this one, we can see the experimental results where the PWM scheme A and E both have number of turn-on actions with the 0 voltage switchings. They both have the same, so there's no gain between either of them. The number of the turn-on actions with non-0 voltage switching are the same. So that's again no advantage of one over the other. But on this one, number of the turn-on actions with high voltage transitions, type A only had 4 and type E had 8. And this is when the losses are actually coming in, because when they're having the switch, when the voltage is high and the current is high, then that's power right there that is being lost. And also, the number of turn-off actions with low voltage transitions in the range is, again, on this one, the type A has 2 and the type E has 0, but let us remember that this is also, when they're saying number of the turn-off transitions with low voltage, this estimate is very minimal, and thus the loss is very minimal compared to that when the voltage is very high. total turn-off losses normalized based on the 6 segment. This one, type A had 1 and type E has 6. And this is a Fourier. This is the experimental spectrum of the input phase on current A and current and type A and type E PWM. As you can see, the type E, which is this was denoted by this one right here, has more harmonics than the A does. Also, the THD was calculated on the A to be 1.54% with a power factor of 0.9993, and the type E has a total harmonic distortion of 2.38% with a power factor of 0.9986. In conclusion, the three-phase matrix rectifiers can be realized with MOSFETs instead of IGBTs for an HVDC and telecommunications applications. Theoretical and experimental results yield utilizing a 6-segment high to low PWM switching scheme, type A, to minimize switching losses, duty cycle loss, and lower maximum output current ripple, while achieving low total harmonic distortion. One of the suggestions that we have for the authors would be that the authors could have better vetted or researched the high to low voltage transitions, as the analysis was used to eliminate type B and D, which was not very well covered. They just went ahead and referenced somebody else's paper and took on with that. Also, more discussion on modern day use case of the matrix inverters and drawbacks of the use and schemes that would be informative to them. One thing that I can say from experience is that these are used more and more, and especially on high current loads and relative high voltage. For instance, one of the applications that I'm very familiar with is right now we have on my work, the current project that is to replace a mechanical type actuation. We're using a hydraulic pump to spin a hydraulic motor, and with that efficiencies of maybe like 70 to 80%. One of the things that we're trying right now, and we're actually prototyping right now, is that instead of hydraulic pump and instead of a hydraulic motor, we're taking advantage of the power density of a 3-phase synchronous motor that we spin with a prime mover, 3200 RPM. That what that is giving us, we're using this type of matrix rectifiers, is we can get a variable voltage output of right now we're using 280 DC volts, that is completely DC, and through that we invert using the same type of inverter, just in the opposite way. Rectifier just in the opposite way as an inverter, to drive electric motors. What this does is we've seen an increased efficiency on the overall system from low 80s to mid 90s. What that does for us is like we can package things in a smaller envelope, and for the customer that is gonna be the end user for this, is gonna be fuel consumption savings, essentially removing the prime mover out and putting a battery, and just do the DC to AC inversion. Yeah, it's like I say, this is a work in progress. We still in the infancy, but it's yielding great results right now. Thank you very much for your time, and if any questions, please feel free to leave any comments. And we apologize for the delay on the video since we had a little bit of technical difficulties. Thank you.